This next podcast is called Rational Functions, Domains, and Asymptotes. Let's begin with the definition of a rational function. A rational function y equals f of x is a function whose form is p of x over q of x, where both p of x and q of x are polynomial functions. So it's got to be a polynomial over a polynomial. Now you could easily have a quotient p of x over q of x where they weren't polynomials, but in our terminology we would not call that a rational function. So we're going to assume if we've got a quotient, it will be a quotient of polynomials. Otherwise it's not considered a rational function. Now let's talk about domains. You've got a quotient here, so clearly x's that make q of x equals 0 are going to be thrown out of the domain. So let's take a look at them. It says domains of rational functions. The domain of a rational function is all real numbers which are not zeros of the denominator. So we're going to take all real numbers in. In other words, we're not going to consider square roots of negatives, because if there was a square root in p of x or q of x, it wouldn't be a polynomial, because a square root is a half power. Polynomials have to have integer powers. So let's take a look at this first one, and what value of x could make the denominator 0? Well, clearly x equals 0 makes the denominator 0, so that's what we throw out. So we could say that the domain of f is the set, the little curly bracket means the set, of numbers such that, vertical line means such that, x is not equal to 0. Or you could put it this way in interval notation. Negative infinity to 0 not including 0, union 0 to infinity not including 0. Let's take a look at the second function. This one is x plus 4 over x squared minus 16. I change the x squared minus 16 to x minus 4 times x plus 4. There are two values of x that make the denominator 0. That's x equal 4 and x equal negative 4. So in interval notation, the domain would be negative infinity to negative 4, leave out negative 4, union negative 4 to 4, leave out the negative 4 and the 4 with the open brackets, and then union 4 to infinity. The third function here that we're going to look at is x plus 4 over x squared plus 16, and the question is, what values of x make the denominator 0? Well, what we're talking about here is graphing, and to graph you have to be using only real numbers, because the x and the y-axis are real number axes. So since this has to be a real number, you can't square it and get a negative. If you square it, it's got to be positive, and if you add it to 16, it's got to be bigger than 16. So there are simply no values of x that make the denominator 0. Negative 4 would make the numerator 0, but that has nothing to do with domain. So here it would be all numbers, or you could say the real numbers. Sometimes they'll do like a double R like that and call it the real numbers. But all numbers would be in the domain here. There's no x that's illegal. Okay, the next thing I want to do is talk about the zeros of a rational function. What values of x make it 0? And you have to recall something about fractions. The only way for a fraction to be 0 is to have the numerator 0 when the denominator is not 0. 0 over 5 is 0, but 0 over 0 is undefined in math. So in order to have a 0 of a function, the numerator has to be 0 when the denominator is not 0. So let's take a look at the first one. This one cannot have a 0 because the numerator cannot be 0. No x intercepts. 0 is the same as your x-intercept. Let's take a look at the second one. Can you have a 0 of the numerator which is not a 0 of the denominator? Well, the denominator is x minus 4 times x plus 4. So the only 0 of the numerator is also a 0 of the denominator, and that's negative 4. And if I let x be negative 4, I don't get 0. I get 0 over 0, which is undefined, so again, no x-intercept or no zeros for that polynomial. Let's go on to the third one. Now, we discussed this x squared plus 16 on the last set of exercises, and we said that since we're dealing with real numbers, x squared plus 16 has to be at least 16, and that would be if x was 0. If x is anything else, it's bigger than 16. So nothing makes the denominator 0. Negative 4 makes the numerator 0. So negative 4 is a 0, or you could say f of negative 4 is 0, or negative 4 is the x-intercept, which is the same as a 0. And then on the last function, if I factor the numerator, I get x minus 4 times x plus 4. That's over x plus 4. Now, what makes x plus 4 0 is when x is negative 4. So negative 4 is not going to be a 0 here. It is a 0 of the numerator, but it's also a 0 of the denominator. So it's not a 0 of the function. It makes the function undefined. However, if you make x plus 4, this becomes a 0. There's no 0 on the bottom. If x is a plus 4, this is an 8 on the bottom, so you get 0 over 8, which is 0. So you could say f of 4 is 0, or 4 is the x-intercept. So we've talked about domains, we've talked about intercepts or zeros of functions. Let's talk about vertical asymptotes. And to help with this, we're going to actually graph the function f of x is 1 over x. And I've made a table of values for it right here. And it's a pretty easy table of values. If f of x is 1 over x and x is 4, then y or f of x is 1 over 4. If x is 3, it's 1 over 3. If x is 2, it's 1 over 2. If x is 1, it's 1 over 1. If x is a half, f of x is 1 over a half, which is 1 times 2 over 1, which is 2. And if x is a third, y is 3. And if x is a fourth, y is 4, etc. Now over here I've graphed that. Here, if x is 4, y is a fourth, right here. If x is 3, y is a third, which is a little higher than a fourth. If x is 2, y is a half, that's a little higher than a third. And if x is 1, y is 1 over 1, which is 1. So that would be right there. Now, if x is a half, then y is 2. If x is a third, y is 3. If x is a fourth, y is 4. So you get this picture of this, whoops, I kind of missed it there, of this smooth curve coming through these dots. Notice the curve here gets closer and closer to the x-axis, but never touches it. Same as here. When you have a straight line, and you have a curve that gets closer and closer to the line, but doesn't touch it, that line is called an asymptote. So the x-axis here would be a horizontal asymptote for this curve. I don't like this top part. I think I'll draw it in a little bit better here. And similarly, the y-axis is a vertical asymptote, which is what we're talking about. So the further you go with this function, the closer it gets to the y-axis, but it never touches it. So that's what we mean by a vertical asymptote, and that's going to be helpful to us in graphing. Now we can complete this graph with a simple observation. If I take f of negative x, which is how you test for symmetry, I get 1 over negative x, which is negative 1 over x, which is negative f of x, which means this is an odd function. Or you can just say, well, the power of x is odd, therefore this is an odd function. Odd functions are symmetric in the origin, which means if you rotate it 180 degrees, it doesn't change. So this end of the function has to look like this. And now if I take this thing and turn it a half of a turn, this cup here will lay on this one, and this one will swing around and lay on that one, and it won't change. So that's my complete graph. Notice the y-axis is a vertical asymptote for the curve, the x-axis is a horizontal asymptote, but we're interested right now in vertical asymptotes, so we'd say our vertical asymptote is x equals 0, which is another way of saying the y-axis. Let's take a look at vertical asymptotes here. Are there any zeros of the denominator which are not zeros of the numerator? Well, not negative 4, that's a zero of the numerator also. But from this second factor, positive 4 is a zero of the denominator, which is not a zero of the numerator. So our vertical asymptote would be at x equals 4. Let's take a look at this third function. Again, and the reason I put up this third function is because I want to show you what happens when a zero of the denominator is also a zero of the numerator. If x is unequal to 1 here, these two factors cancel each other. Now if x is equal to 1, this is undefined, but if it's unequal to 1, they cancel, so y is just 2x plus 1, which is this straight line. It has y-intercept 1, and its slope is 2. So if I rise 2, I run 1. If I rise down 2, I run negative 1. So that's the line. But what happens when you hit x equal 1? Well, you become undefined, so it like punches a hole in the graph, and then the graph continues on. So the reason that a 0 in the denominator, which is also a 0 in the numerator, is not a vertical asymptote is because it's just punching a hole in the graph. Now let's go on to our last topic, which is horizontal asymptotes. Here again I've written my p over q, and I've written out the function p and the function q in descending powers of x. So x to the m is the biggest power of x to the n is the biggest power of x in q. How do we tell if we have horizontal asymptotes? Well, we compare the degrees, the biggest power of the polynomials. And the rule is this: if the degree of the top is smaller than the degree of the bottom, then y equals 0, or the x-axis is a horizontal asymptote. So here, the x-axis would be a horizontal asymptote because the degree of the top is 1, the degree of the bottom is 2. If the two degrees are equal, then the quotient of the lead coefficients is the asymptote. So in example A, the power of x here is 2, the power of x here is 2, so the asymptote is y equals 3 over 1, or y equals 3 is our horizontal asymptote. That would look like this. Y equals 3 would be our horizontal asymptote. In the last example over here, the top factors to x minus 3, x plus 2. That's really not important to us, though. We're not looking for zeros. That's what we do if we were looking for zeros. We just need to know what's the lead coefficient on the bottom, so I went ahead and multiplied this out. This is the same as 2x squared minus 4x minus 6. Again, the powers are the same, top and bottom, x squared over x squared, so the horizontal asymptote would be y equals 1 over 2. It would look like this. If that's 1, then there would be your y asymptote. Now we'll see how we use these asymptotes, vertical asymptotes, zeros, etc., to graph when we look at the next podcast on graphing rational functions.